All right, kiddos, fasten your seatbelts because this is going to be a practice problem filled video. Okay, so this first problem wants us to calculate the pH of a 0.0023 molar solution of hydrochloric acid. Okay, you'll remember that hydrochloric acid is a strong acid. That means when it dissolves in water, it completely dissociates into H plus and Cl minus. Okay, that means look at this mole ratio. Every 1 mole of HCl that you dissolve, you get 1 mole of hydrogen ions out. Okay, so in 1 liter, if we have 0.0023 moles of HCl, we would have the same concentration of hydrogen ions, right? So this means, because this is a 1-to-1 ratio, this means that our hydrogen ion concentration is equal to 0.0023 molar. Okay, so if we want to find the pH of that, we need to remember the pH is equal to the negative logarithm of our H plus concentration. Okay, so in this case, the pH is going to be equal to the negative logarithm of 0.0023. Okay, so when you put this in your calculator, make sure you're hitting the regular log button, not the natural log button here. We want just regular old log. Okay, so we need to take the negative. Make sure you hit the negative sign, not the minus sign. Okay, use the negative sign. Negative log of 0.0023. And we get this big number. Okay, we need to think about sig figs. Remember, however many sig figs are in your original number, that's how many sig figs will be in the mantissa, or the after the decimal portion of your pH calculation. Okay, so we had 2 sig figs here. That means we need to have 2 digits after the decimal. So this pH is going to round off to 2.64. Okay, another quick way you can verify this, well, it's hydrochloric acid, so it should definitely have an acidic pH. Okay, that's less than 7, definitely an acid. Okay, good to go. Now we have a similar problem. Okay, but now we have nitric acid. Same thing, it's a strong acid, meaning it dissociates into H plus and NO3 minus ions completely. Okay, if that's the concentration of the acid, because this is a 1-to-1 mole ratio here, that also means that our hydrogen ion concentration is 0.00456 molar. Okay, same thing, pH is the negative log. Now this has 3 sig figs, right? That means our mantissa, or after the decimal, needs to have 3 sig figs as well. So we're going to take the negative log of 0.00456. Now we're going to have 3 sig figs. So this would say the pH is 2.341. And again, I've underlined to kind of show this is a new sig fig rule here, right? 3 sig figs, 3 digits in the mantissa. Okay. The next problem, we're dealing with sulfuric acid now, okay? This one, think about how it dissociates. How many hydrogen ions is it going to give off? H2. This is going to give off 2 hydrogen ions and 1 sulfate ion. Okay, so now the hydrogen ion concentration is going to be twice as much as the acid concentration, right? So now we need to say our hydrogen ion concentration is going to be 2 times the acid's concentration. Okay. So that's our hydrogen ion concentration. To find the pH, negative log we have 3 sig figs here, so we want 3 digits after our mantissa, 1.815. Okay, hopefully that's pretty clear. Just remember our formulas here. Okay, these were all three of these that we've done so far, strong acids. Okay, so remember we used that equation so far. Okay, this next one is going to bring in, previous concepts. Calculate the pH of a solution made by dissolving 2.38 grams of hydrochloric acid into 1.25 liters of solution. Okay, we need to know the hydrogen ion concentration, but before we do that, we need to know the concentration of our acid, which you'll remember is moles per liter. Okay, so we need to figure out how many moles we have. Okay, you could do the molar mass calculation. If you're me, you memorized it. Oops. Okay, so our number of moles is, I'll round for sig figs at the end here. We have that many moles of HCl dissolved into 1.25 liters. So our moles per liter is 0.00, let's see, 3 sig figs, 3 sig figs. So we'll round this to 3 sig figs. 0.00522. I'm sorry, 0.0. Did I say 00? I don't know. 0.0522 molar. Okay, and that's the concentration of our HCl. But of course, it's a 1-to-1 ratio between HCl and hydrogen ions. Okay, so that's also going to equal our hydrogen ion concentration. Okay, and this is a strong acid, so the pH is equal to the negative logarithm of that concentration. 3 sig figs, so we're going to need 3 decimals after our 3 digits past the decimal. 1.282. Cool beans, easy peasy. Okay, hopefully these have been pretty straightforward so far. I'm not going to do this one just for time's sake, but I know you could, right? The only thing that's different now is we have H2SO4, so when you'll find the molarity of the H2SO4, but then when you go to find the concentration of the hydrogen ions, remember that it's going to be twice the concentration of our sulfuric acid. So that's going to affect that pH. Okay, and this next problem, now we're getting into the pOH stuff. Okay, what happens if we have a base? Okay, first thing is to calculate the pOH of a 0.056 molar solution of sodium hydroxide. Okay, so we will remember that when sodium hydroxide dissociates, we're going to get a sodium ion and a hydroxide ion, right? So now we can see this from our base to our hydroxide is a 1-to-1 molar ratio. Okay, so for this example, we can conclude that the hydroxide ion concentration would also be 0.056 molar. And now we need to remember, how do we find pOH? Well, pOH is the negative log of the hydroxide ion concentration. Okay, so this is a new formula for this sample problem video. Okay, so for strong bases, we can find the pOH. Oops, sorry. So in this case, it would be a negative log 0.056. Two sig figs here, so we want 2 digits in the mantissa, 1.25. You'll notice there's no units for pH or pOH also. Okay, they are unitless. Okay, that's our pOH. Good. Now there's sort of 2 things you could do. Okay, you could either find your hydrogen ion concentration by taking Do you recall KW from our equilibrium chapter? Or no, I'm sorry, from last unit, dang. Not last unit, last video. Oh my goodness gracious, okay? Hydrogen ion concentration is KW over hydroxide ion concentration, so you could solve for that and plug back into our pH formula. Okay, or you could, make your life a little easier and just remember that 14.00 always equals the sum of your pOH and your pH. Okay, so if you know your pOH, you know that the pH is going to equal 14 minus that pOH value. Okay, and you just want to make the sig fig, the sig figs match up. So 2 digits past this mantissa, we're going to do the same thing for our pH. So now we would say our pH is 12.75. Okay, and think about what this means. Okay, remember pH, it's the pH scale, you guys, it's not the pOH scale. Okay, so anytime you're comparing to verify that it's acidic or basic, okay, please reference the pH for that. Okay, I get kids who want to compare pOH values and be like, wait, it's an acid. Okay, no, that's the pOH. It's not the pOH scale, it's the pH scale. Okay, so on the pH scale, this pH is definitely basic, right? It's really close to 14. Basic solution, sodium hydroxide, boom, done. Okay, let's try a couple more. So I'm not going to do this one because it's very similar to the one we just did. Okay, but now let's look at what if we had calcium hydroxide? Well, calcium hydroxide, when it dissociates in water, you're going to get calcium ion, and you're going to get 2 hydroxide ions, right? So that means for every 1 mole of calcium hydroxide present, it's going to give off 2 moles of hydroxide. So our hydroxide ion concentration would be twice this concentration. We'll round it off to 3 sig figs. Okay, so that's our hydroxide ion concentration. From there, we could find the pOH. It's going to be the negative log of that hydroxide ion concentration. One 1.747. Okay, but the question doesn't want the pOH, it wants the pH. Okay, no biggie. pH is going to equal, I'll put 3 digits after my 14 to keep the 3 decimals after my, in the mantissa here. We get 12.253. For our pH, okay, that's a basic pH. Calcium hydroxide is a strong base. Bada bing, bada boom, easy peasy lemon squeezy. Okay. Then we get into some of the opposite stuff where now I give you the pH or the pOH and you have to find the ion concentration. Okay, so here we have what's the hydroxide ion concentration if your pH equals 2.45. Okay, for this now we have a new formula that you need to remember. Okay, you need to remember that the hydrogen ion concentration is equal to 10 raised to the negative pH. Okay, and that's through that magical math of logarithms. Okay, that if you ever understand, come back, visit your alma mater, and help a woman out. Okay, so to solve this, we have our pH. We're looking for H plus. It's going to start, my brackets get really ugly, I apologize. Equals 10 to the negative 2.45. Okay, so now if we plug that in, 10 raised to the, okay, now we have to use our little caret button. Negative, please make sure you input that negative. Okay, otherwise you're going to get crazy high answer. Negative 2.45. Get 0.00354, blah, blah, blah. Okay, sig figs, hold up. Now we got to go backwards. We had 2 decimals in the mantissa. That means our answer should have 2 sig figs. Okay. 0.0035, and now it's a concentration, so you need to make sure you include units of molarity or molar. Okay. Calculate the hydroxide ion concentration of a HCl solution with a pH of 4.25. All right, now we need to remember that hydroxide ion concentration is 10 to the negative pOH. And then we're going to bring back an oldie. Don't forget that pH and pOH added together always equals 14. Always, always, always. Okay, so if our pH is 4.25, you can go about this 2 ways. Okay, you can first calculate the pOH. Which would be 9.75. Okay, and then from there you could use this formula. And you would get 1.78 times 10 to the negative 10th molar. Okay, so that's more of a straightforward way to do it. Okay, but or you could do it a different way. Ouch. You could remember that your hydrogen ion concentration is going to be equal to that ion product constant for water divided by the hydroxide ion concentration. So you could take Kw over, whoa, hold on. You guys, I got confused. I thought I was doing a different problem. Because you would need that. Never mind. Ignore me. I'm recording this video at 6:30 in the morning, so please have some mercy. Okay. Never mind. You couldn't use that because you would need hydroxide ion concentration. Anyways, so that was a dumb thing on my part. Okay. So you have the pH, find the pOH, plug the pOH back into this equation. Oopsie daisies. My apologies. But you know what? It's not worth me recording an entirely new video. Okay? Y'all can get over it. I know you can, because you're forgiving little angels whom I love. Okay. Calculate the hydroxide ion concentration of sodium hydroxide solution with pH equals 11.5. Okay, that'd be very similar to what we did up here. Okay, you could find the pOH by subtracting. 10 to the negative pOH is going to give you that guy. This is the one I was thinking of. Okay, calculate the hydrogen ion concentration of a sodium hydroxide solution with a pH of 12.50. Okay, so we're going from no, I wanted this to say pOH. Change that to pOH. We're going to make it more complicated. Okay, so if we have our pOH, we could easily find our hydroxide ion concentration, right? 10 to the negative pOH, 10 to the negative 12.50. We want to keep 2 digits. No, keep 2 sig figs. So we would say 3.2 times 10 to the negative 13th molar. Edit these sig figs. I'm a ding dong. 2 sig figs there. Okay, so that's our hydroxide ion concentration. Okay, so this is what I was talking about. Now you could say You could bring back this oldie but goodie. Okay, and you could say, you could do it this way, and you would get that your hydrogen ion concentration is 0.031 molar. Okay, or now you could do the subtraction and you would say your pH is 14 minus that original POH. And then you could say your hydrogen ion concentration is 10 to the negative pH. And you would get very similar answer, right? You would still get 0.031 molar, okay? So you can see that this relationship is related to the properties of acids and bases, but you can also use your pH and POH add together to 14 as well. You should get the same answer either way you look at that. Okay, we've got one more to do real quick, and this one is just kind of working backwards using everything we know. Okay, so how many grams of sodium hydroxide are dissolved in 500 milliliters with a pH of 13.68? Okay, so we can find all sorts of things, right? We can find our POH. Okay, if we know our POH, we could do our hydroxide ion concentration, 10 to the negative POH. So our hydroxide ion concentration would be 0.48 molar. Okay, think about that. Think backwards. 1-to-1 mole ratio, right? So if our hydroxide ion concentration is 0.48 molar, guess what? Our sodium hydroxide concentration must also be 0.48 molar or 0.48 moles per liter. Okay, well, we have 500 milliliters or 0.5 liters. Okay, this is kind of a flip-flop t-chart, my bad. But we could figure out, right, that our number of moles present must then be 0.24 moles of sodium hydroxide. Molar mass, I think it's 40. Quick check. 22 point. Where's that potassium? Hold up. Boom. Okay, so again, what we did is we took the pH, we found the POH. From the POH, we could find the hydroxide ion concentration. If we understand the dissolution of this substance, we can see that the concentration of sodium hydroxide would also be 0.48 molar. If you had half a liter of 0.48 molar, you would have 0.24 moles of sodium hydroxide, molar mass conversion to grams. Okay, so that's a lot of practice problems. That should be plenty to get you through your OWL.